Okay, so maybe we should start the last session of the day. So our first speaker is going to be Tom Banks, and he's going to be giving us the talk by Skype. So please refrain all the questions till the end, and then I'll pass. It's very important at the end you wait for the microphone, because otherwise he will not be able to hear your question. Okay, and speak as loud as you can. All right. Okay. So. All right, Tom.
Okay. Should I start? Okay. So first, I'd like to thank the organizers for inviting me. I'm very sorry I can't be there with all of you. My talk today is going to be about the limits of effective field theory, which is a subject I've been thinking about for almost 2 decades, all of the 21st century. And the traditional answer to that question is shown on this slide. And I've noticed that almost all of the talks at this conference so far have sort of assumed the traditional answer one way or another. I'm going to be arguing to you that the traditional answer is incorrect, and that there are actually classical indications already that the traditional answer is wrong. And the strongest ones, as far as I'm concerned, are listed here and on the next slide. Traditional field theory, quantum field theory arguments do not account for the finite entropy of de Sitter space and black holes. The large increase in the local entropy of black holes when light particles are dropped onto them. And this is something that's true only for black holes in Minkowski space, de Sitter space, or in anti-de Sitter space when the radius of the black hole is much larger than the anti-de Sitter radius. So it's a very different thing than the large ADS black holes most people study. The other thing that follows simply from the metric of Schwarzschild de Sitter is that local excitations decrease the entropy of de Sitter space, something that local field theory simply cannot explain. But I think the clue to all of this stuff was given to us in 1995 by Ted Jacobsen. Ted showed that you could almost derive Einstein's equations from the following principle. This is not quite the way Ted stated it, but it's equivalent. If you use the Bekenstein area law for the holographic screen or maximal area surface in the foliation of the boundary of a generic causal diamond in space-time, and assume that the entropy associated with that diamond is given by the area in Planck units divided by 4, and use the first law of thermodynamics, then you get Einstein's equations. This implies that we should think of field theory as the local form of thermodynamics, otherwise known as hydrodynamics. And one of the things I want to remind you about hydrodynamics is that it's useful in 2 different regimes. If I have a system with a ground state, it's very often the case that the low energy excitations of the ground state are described by quantized hydrodynamics, phonons and other sorts of quasi-particles. But hydrodynamics as a classical theory is valid also in regions of high entropy, and indeed that's how it was invented originally. And in that regime, quantizing hydrodynamics is a bad idea. It's not the right thing to do. The microscopic quantum dynamics is very different, but the classical hydrodynamic equations are true on large scales. The final thing that you learn from this is that the cosmological constant is not a local energy density, because the one term in Einstein's equation that Jacobsen's derivation cannot give you is the cosmological constant. Ted thought of this as a bug. I think of it as a feature. Willy Fischler and I have for years been suggesting that the real definition of the cosmological constant is the following. If I think about causal diamonds in space-time, they have 2 invariant measures of their size. the maximal proper time in the causal diamond, which is the length of the geodesic between its tips, and the holoscreen area, the area of that maximal surface. And the cosmological constant controls the relationship between those two asymptotic limits. Now, this way of thinking about things resolves two problems in the field theory treatment of classical horizons. First of all, it says, not surprisingly, the de Sitter vacuum is a maximal entropy state because it is the typical state of the system which is defined to have a maximal total entropy in a finite maximal size causal diamond. The typical energy scale of those excitations that are responsible for that area is 1 over the de Sitter radius. The black hole entropy formula in de Sitter space implies that localized excitations are constrained states of that maximal entropy state. They have a number of constraints that's equal to the localized energy times the de Sitter radius. And this gives you a classical derivation of the Gibbons-Hawking de Sitter temperature, which was originally derived from quantum field theory. Another problem that's resolved by this point of view, and one that I think is really extremely important in view of a lot of recent activity, is that there are transitions between larger black holes and smaller black holes. You drop a very small piece of matter onto a large black hole, and all of a sudden, and again, this depends on the specific heat being negative, all of a sudden there's a huge increase in entropy. That means that a small black hole plus a small particle dropped on it is a constrained state of a large black hole with about E times R constraints, where E is the energy of the system that you are dropping onto the black hole, and R is its Schwarzschild radius. This explains not only that classical fact, but it completely resolves the firewall problem, because it takes a time of order the Schwarzschild radius to unfreeze those constraints. And during that period, the small system that's been dropped onto the black hole remains isolated from the black hole and non-interacting, because you have, in order for it to interact, you have to unfreeze those constraints. And the details of that depend on specific models, but the general idea is encapsulated in what I've told you. Now, if de Sitter space has a vacuum that's a maximal entropy state, and I take the limit of de Sitter space to be Minkowski space, then that suggests that the Minkowski theory does not have a vacuum that's unique. It's in fact also a maximal entropy state with an infinite entropy. I want to point out that the anti-de Sitter space limit gives you an identical picture of a Minkowski diamond. Let me remind you of the concept of the Susskind-Polchinski arena, which was the context in which one first tried to relate correlation functions in anti-de Sitter space to scattering amplitudes. And if I look at most states in anti-de Sitter space, and I look at some arena, some particular small causal diamond, I'm assuming the anti-de Sitter radius is much larger than any microscopic scale. And I look at a causal diamond that's large but small compared to the anti-de Sitter radius, then that diamond has a finite area. And it's also clear from the general ADS technology that that diamond is in its vacuum state, because most things that I do on the boundary of anti-de Sitter space won't impact that particular diamond. So now let's just assume that that diamond has a finite dimensional operator algebra, a finite dimensional Hilbert space, given by the covariant entropy principle. Then Page's theorem implies that the density matrix of the diamond is maximally uncertain, with probability exponentially close to 1 in the following sense. The entropy of an entire conformal field theory is, of course, infinite, but if I put in a UV cutoff, as implied by taking a finite but very large radius diamond in anti-de Sitter space, a radius large compared to the anti-de Sitter radius, but fixed, then I have a large finite entropy system entangled with a much smaller entropy system. And Page's theorem tells me that they're usually maximally entangled, which means that the smaller system is maximally uncertain with probability exponentially close to 1 as I take the diamond cutoff of the big diamond to infinity. So the de Sitter and anti-de Sitter limits that give you Minkowski space agree. Minkowski space does not have a unique vacuum, and localized states in the system must therefore be constrained states of that large vacuum ensemble. Now, there's a very picturesque way to understand these constraints via scattering theory. I've advocated in a few papers over the last few years the point of view that scattering theory should be thought of always as a map between current algebras in the past and the future. And there's a way of doing this that applies equally well to field theory and to quantum gravity, even though there will be special different circumstances in the two cases because of the nature of the excitations in those two different kinds of theories. So the first thing I want you to do is view the conformal boundary of Minkowski space via its Fourier transform. The Fourier transform of the conformal boundary of Minkowski space is the momentum null cone that consists of massless momenta either coming into or going out of, in the future, the standard Penrose diamond. The momentum null cone describes only massless particles, but if I, in addition to talking about null momenta going into and out of the diamond, I allow null momentum that runs along the boundaries of the diamond, then I can also describe massive particles in this formalism without worrying about the fact that time like infinity is a singular point in the usual Penrose picture. The only singular point in this picture is the p equals 0 point where the null cone pinches down to nothing. Now, if you think about currents on that null cone, there's a minimal set of currents that you have to have if you have any spin, half-integral spin particles in your theory at all. And namely, they're things that look very much like the supersymmetry currents. And you could have both left-moving and right-moving ones. The minimal set would be just left-moving ones, which would imply that all the particles that carried that spin were massless. But we don't need to do that. You can describe both situations by an appropriate current algebra. The algebra of these generators, Qi alpha of P, was first worked out many, many years ago in the 1980s by Awada, Gibbons, and Shaw. And it's essentially unique given the insistence that fermionic half-integer spin operators anti-commute at space-like separation, and that we obey the constraints of Lorentz invariance. A scattering representation of that algebra is one that satisfies the following constraints. It'll be a space of what I call exclusive Sturman-Weinberg jets. I hope most of you know what a Sturman-Weinberg jet is. The experimental side of our field works with these things all the time. The basic idea is that I take these smeared, these current operators, which are local in momentum space, and I smear them with some functions. And I'm going to have an acceptable state in a scattering representation only if that smeared thing vanishes for f's that that don't satisfy the following conditions. F, for non-zero magnitude of the momentum, has to vanish outside a finite number of caps of finite opening angle. The capital bold-faced N in this formula is the unit vector that describes the direction on the sphere through which the momentum is going out. At p equals 0, we have to insist that these operators vanish unless F at p equals 0 vanishes in a small annulus around each of those spherical caps. Now, no momenta are of the form p, where p is a positive number, times plus or minus 1, and then plus or minus the unit vector n. Those describe, first of all, the plus or minus 1 describes things that are either coming in from the past or going out in the future, except that if I change the sign of the n, they are traveling along the light cone rather than going in or out of it. So again, I repeat, if you have massive particles, you also need momenta like that. Here's a picture that shows you what these constraints consist of. The red circles, so this is supposed to be the surface of the sphere. I'm sorry, I can only draw circles. The big sphere in the dark blue represents the entire sphere at null infinity. On that sphere, it's colored dark blue because I'm allowing for every possible configuration of zero momentum particles, to use a word that I will claim to you is just an approximate description of things, coming out in all of those possible directions. I'm insisting that in the light blue circles that surround the small red circles, that contribution goes to 0. The way to describe that in the language of experimental particle physicists is that we have a jet isolation criterion. If we have a jet of particles coming out at some finite opening angle, carrying finite energy, if there happen to be some very low momentum particles coming out nearby that jet, you just widen the aperture of the jet to include them in such a way that eventually you get to a place that there are none. And the content of the description of the Hilbert space that I gave you is that we don't allow states where there's no region around each red circle with no zero momentum particles. The red circles, of course, are jets, and they're red to explain to you that they're hot, they carry momentum and energy. Now, in the Sturman-Weinberg prescription, one sums over all the quantum states of the zero momentum stuff, but in what I'm proposing, you have to keep track, and the operators Q at p equals 0 do keep track of the quantum states of the zero momentum stuff, and that's what carries the huge amount of entropy that my previous arguments suggested to you. Now, all of this that I've just described to you is not something that I believe is currently mathematically well-defined at the moment. There's, even at the level at which we have mathematically defined quantum field theory, what I'm suggesting here is not mathematically well-defined, but to define it, you can regularize it by backing off from null infinity and going to a finite causal diamond. And let me tell you how I do that. These spinor generators are replaced by finite number of fermionic operators that have the property that they contain only angular momentum up to some cutoff, which is the size r m Planck, where r is the holographic screen radius of this finite causal diamond, which is the r is supposed to be taken large, and we will define the theory by taking the limit r goes to infinity. the bilinears in Q, you get the Q's as thought of as a function of these angular momentum labels, M, it's a totally antisymmetric tensor with d-2 indices. The d-2 is telling you about the dimension of the holographic screen. And if I take a pair of these Q's and contract together all of their indices but one, I get a matrix. And those bilinear matrices in Q's are the things that we put into the Hamiltonian. And the Hamiltonian is a single trace operator made out of those matrices. The constrained states that I was talking about are defined quite rigorously in this framework as in the following way. You take the Q's, they have some superalgebra commutation relations, a finite dimensional superalgebra. They don't have to be, canonical fermions, but they have a finite dimensional representation for each value of all of these indices. And the constrained states are those on which the matrix bilinears made out of these Q's are block diagonal. And so the constraints are such that they decouple in a single trace Hamiltonian the different blocks. And that is supposed to be read in the following way. There are some small blocks, B1 through BK, and those small blocks you think of as the red circles or the jets in the picture. And then there's a very large block whose size is of order L minus the sum of the BK. And when I count up all of the constraints that I have to put on the Q's in order to make these things block diagonal, it turns out that there are the sum of BI to the d-3 times L constraints. It's not exactly that. That's how it behaves when L goes to infinity. L goes to infinity, I remind you, is the limit that we're going to Minkowski space from a finite causal diamond. And you can show explicitly that with the appropriate normalization for this Hamiltonian, these constraints will continue to be valid on smaller and smaller causal diamonds as long as the following inequality is satisfied, that the sum of BI to the d-3 times L is much, much less than L to the d-2. And that's a formula that if you think about it the right way and you call this thing BI to the d-3, or rather the sum of BI to the d-3, if you call that energy, this is exactly the constraint you get in just by thinking in general relativity of sticking energy in the form of particles into a finite causal diamond, and you ask when I've got enough energy to make a black hole of the size of the causal diamond. So the jet interpretation of constrained states only makes sense when this inequality is satisfied. Jet interpretation means that these block diagonal pieces don't interact with anything else. This equation all by itself, I can't tell you the details about this, but Fischler and I have written of order 10 or 15 papers trying to explain this. This by itself, I claim, explains qualitatively the scaling behavior of the temperatures of horizons and the time scales of scrambling. And the models that we've written down are what Susskind and Sekino called fast scrambling, and Hayden and Preskill showed had to be the behavior of black hole physics on the horizon in order to account for the properties of quasi-normal modes. I don't have time to go into more details about that. Let me go on to the use of these ideas in a model of inflation. Now, I would claim that inflationary fluctuations imply, the size of inflationary fluctuations that we've seen, imply that the entropy bound that I talked about, the maximal entropy being given by the area of a diamond, is close to being saturated inside the inflationary horizon. And I would claim that's the limit at which you no longer believe effective field theory. Effective field theory is a good approximation only when, in the sense I've tried to convey in the last couple of slides, the amount of localized stuff in the diamond is much less than the total entropy that one has in the system. And that's simply just by the count of the size of the fluctuation. It's very unlikely to be true during inflation. So the holographic space-time models that I've told you about give you some insights into a number of cosmological questions. One of them is that if I don't put any constraints on the initial conditions at all, what I've just told you tells you that the universe should evolve from one maximal entropy state to the other as time goes on. And since we seem to have experimental evidence that the universe ends in a de Sitter space, which, at least as long as it lasts, is a system that can only have a finite amount of entropy, that means that the system will always look like it has no localized excitations in it, because localized excitations are constraints. So if you insist on a certain amount of energy in the asymptotic de Sitter space, the most probable constraint with a fixed amount of energy is just to have a single black hole. That's not a terribly interesting cosmology. You can make them all like that, and it won't do anything like the cosmology that we see around us. We've conjectured that the most probable initial condition that leads to a radiation-dominated era at some time during the history of the universe is a dilute gas of black holes with the maximal homogeneity that's allowed by the fact that we're doing quantum mechanics. The systems that describe these black holes are systems that have a certain amount of entropy, which determines how big the fluctuations are going to be, because one of the kinds of fluctuations that can occur is you can spontaneously get into a state that's frozen. And so you can have less entropy. And when the entropy is small, the probability for that is not so terribly small. And so there will be small fluctuations in what we view thermodynamically as the entropy of these black holes. And our claim is that those are the fluctuations we see in the sky in the cosmic microwave background. Now, on the next picture, I want to show you the kinds of time slices that make sense in this quantum model of cosmology. You have to have time slices that take place inside a causal diamond. So they can't be the usual FRW slices, which are a global description of space-time. The time slices, if we're going to build in the constraint of causality, have to be such that the Hamiltonian that describes what's inside a small diamond, unfortunately, I don't have a pointer here, but if you look at one of the smaller diamonds in this picture, you want it to be true by causality, that as I follow along the time-like trajectory traced out by the tips of these diamonds, that the degrees of freedom inside the smaller diamonds remain decoupled from the ones outside for the period that that diamond lasts. And then you gradually couple in more and more and more degrees of freedom as time goes on. In order to do that, the Hamiltonian must be time-dependent. And you can see from the picture of the time slicing, even if we were discussing Minkowski space here, with this kind of causal time slicing, the time evolution, the killing vector that describes, the vector field which describes time evolution is not a killing vector. So energy in this description of things is only an asymptotic conservation law. And in fact, it's given by the number of constraints that the system satisfies out at the boundary at positive infinity. Okay. Now, I can't tell you about the details, but if you remember the formula for the scalar fluctuation amplitude, zeta equals delta H over epsilon h, where epsilon is the slow roll parameter, and h is the curvature, the scalar curvature on the co-moving time slices, then you can use this formula. In our model, delta H over H is time independent, unlike field theory models, because delta H over H is just given by this universal black hole entropy formula. And so we get different formula for, as a function of the slow roll, I call it the slow roll parameter, but in fact it's the whole slow roll metric. You get different formula for the different correlation functions. But all we've ever fit in experiment is the 2-point scalar correlation function, and we have so far no other constraints on what that slow roll metric is. So given that the model gives you approximately de Sitter invariant correlation functions, which is true, but I do not have time to explain it here, then you find that as far as the 2-point function is concerned, we can fit the slow roll metric to the data just as well as you would fit the slow roll metric from your favorite field theory model of inflation. The predictions then for other correlation functions, like the tensor 2-point function and the higher point functions, are definitely different in this model than they are in slow roll inflation. It might be that they're very small. The tensor 2-point function, the traditional ratio of tensor to scalar fluctuations, scales like epsilon squared instead of epsilon in this model. And if the order 1 coefficients are not large, that suggests that the tensor 2-point function will be very small. We don't at the moment know how to calculate the order 1 coefficient, so that's a big defect compared to the field theory models of inflation. But it's not a defect necessarily of the model, it's a defect of its authors. In this model, black hole decay is the source of the hot Big Bang. We've also argued that it's very likely, depends a little bit on your theory of CP violation, that black hole decay can lead to baryogenesis. There's a myth that it can't, but once you take into account the fact that the black hole mass and therefore its temperature are changing with time, there's no CPT argument that says that black hole decay can't lead to baryogenesis. So you have to understand the model of CP violation. And it's possible, and we're working on this now, we don't know how to do this calculation yet. It's possible that these tiny black holes that are implied by this model, by the way, I should tell you that fitting the CMB fluctuations to this black hole entropy formula for delta H over H gives me black holes for, if I take epsilon equal to 1/10, the black holes are 1 million Planck sizes in radius. So they're really, really tiny, and they decay rather quickly. But we've shown that before they decay, they start to clump in a nonlinear way. And it's possible that they will clump so efficiently that they make a population of small primordial black holes that will survive and could either constrain the model, or they could be a source of part or all of the dark matter. The model has very, very few parameters, just about, except for the slow roll metric, that's about it, and the CP violation. It would be very constraining if we could do more measurements, especially if we find that it gives rise either to an unacceptable or an acceptable primordial black hole spectrum, because it would make predictions for what the dark matter is. Okay, well, this is where I'm going to stop. My last slide is just a brief history of what I call in quotes swampland conjectures. as I said at the beginning, I've been making conjectures about why effective field theory is a bad guide to lots of things in quantum gravity for a long, long time. And some of those, I believe, did lead to some of the work on the Swampland and the weak gravity conjecture. So I just thought I'd put up the history. Thank you very much.
So I'm going to ask the audience if you have any question. If you cannot hear it, I'll try to repeat it, okay?
Okay.
So is there any question?
Hi. How can you hear?
Yes, I hear.
Okay. How does the spectral index depend on your slow roll parameters? Will that match with the observations?
Yeah, well, basically what you do is that's what you fit to the slow roll metric. Mm-hmm. So if you think about what you do in inflation, it's basically the same thing. You have some particular model. People call it we fit the potential to the spectral index, but the fitting the potential just means fitting the slow roll metric, because if you give me a slow roll metric, then I can define an energy density and a pressure, and there's an effective scalar field theory with a potential that reproduces that slow roll metric. So basically, when you're fitting the CMB fluctuations, you're fitting that metric.
Okay, thank you. Maybe I can ask another question. So I'm reading here now. So maybe I missed this, but so there was a slide where you said that the most probable initial condition, yes, is this one. It's dilute gas of black holes. So how were these black holes formed?
Okay, so the thing that you have to take your head and turn it around, in the sense that we're always thinking about normal localized excitations, which we describe in terms of particles and how they collapse to make black holes.
Yeah.
That's not the most fundamental way to think about black holes. The most fundamental way to think about black holes is to think about these, the picture that I gave you, let me go back to it. Here, that the localized excitations are described by these diagonal matrices. And if I have a generic state of each little block, each matrix, then that state is a maximally uncertain system with large entropy. And that's what a black hole is. Now, how you interpret that in this formalism depends how these things are moving through space-time. And I haven't had time to tell you about our description of how to move through space-time. But if one of these block diagonal things is just sitting there at rest, and if there were a large number of constraints at infinity that said that this block was decoupled from all the degrees of freedom on the cosmological horizon, then it behaves in all respects like a black hole from all, sort of qualitative thermodynamic ways of thinking about things.
Okay,
so
thank you.
What we say is these constrained states that in scattering theory we just construct, thinking about ourselves as the experimenter out at past null infinity. We just construct these constrained states. In this model of cosmology, you just imagine that the initial conditions were such that you started off with those constrained states.
Okay.
And if you don't do that, you won't have any localized excitations at all. And if you do, the most likely thing for them to be is a black hole And for a given amount of energy, if you want to maximize the entropy of localized stuff, I make it into all one large black hole. This is, again, when I'm in de Sitter space. So that's the origin of black holes is in the initial conditions.
Okay. So, is there any other pressing question? If not, let's thank Tom again. We can proceed.